All right, welcome everyone. So today's technical brown bag, thank you for joining us. We're going to be doing a kind of fun one today and going through our frequently asked questions that we get during calls and meetings with analysts and partners and clients, etc. So Steve Perkins will be presenting that. But with that in mind, please feel free to ask questions throughout the session and we'll get to them live during this call. So thank you so much, Steve, and go ahead and take it away.
All right, thank you very much. Sound check, you can hear me okay?
We hear you loud and clear.
All right, great. So, and you know what? I am going to throw in my video so I make it a little bit more personal so you can see me. Working out of my home office. So thank you everybody for joining. Yeah, as Mary said, we've been doing these for a while and we've been getting quite a bit of takeoff on our business, and we've been collecting questions, and a number of you keep returning to these sessions, so thank you. And seems like we've got some new folks on here too. Again, the goal here is to really talk about, answer a bunch of questions. And so we built a list, and some of them had come in on some of the last calls and we never got around to them. So I thought I would show the questions that we're going to answer up front so that you can figure out if you're going to phase in or out and pay attention in or out. Don't expect you to listen to all this. Excuse me, there's a set of questions just around about TLS that have come up. And then secondly, then we'll move into the discussion around symmetric key intercept itself, and some more detailed questions about that. We've got some new visuals if you've been around for a while, as again, as things are really taking off with our business, the ideas of how to describe and discuss our technology is really maturing. And so we're going to share some of that with you. As you see what is secure, I'm sorry, let me back up. We're going to cover, obviously just a couple of data points on TLS, but methods of decryption. There are some questions about PFS traffic and what's wrong with performance of these systems and what are the issues. And then another look at what symmetric key intercept is, but really how does Nubeva do what we do? How do we get our keys? Once we get the keys, what for decrypted visibility, what can you do with them? There's a bunch of big questions that generally people have about that. There's three big ones we'll cover, and then there's a whole discussion around security scale, and more, especially as we've been seeing a lot of takeoff in the 5G area, but in general with large enterprises, the whole discussion of service mesh comes up, and how does that fit in, and how do we play in or about that. And then lastly, if we have time, we'll get to open Q&A. So with that, I'm just going to plow forward. Mary, I cannot see any Q&A popping up, so I'm going to count on you to stop me if it's relevant. If not, queue them up to the end. I'm going to try to watch my time to get through this very quickly with 10 minutes towards the top, so that I'm assuming you're all really smart up there, and here we go. So I pulled together some interesting stats on TLS, and very interesting. I was talking to a CISO friend of mine a couple of weeks ago, and he was saying, "What are you doing again?" And I told him that we give decrypted visibility of TLS. We enabled visibility into TLS traffic, and he said, "What's TLS?" I said, "SSL." He said, "Oh, I always thought TLS was something different." So any of you might double check that. Some of your higher level execs or older folk might be caught in the past. Obviously, SSL's evolved into TLS, and now we're at TLS 1.3. But some fun facts I pulled off of the internet, not hard to see. I'll let you read through them. About 85 million certs out there, all delivered by about 9 authorities. Still a good number of sites doing SSL 2.0 and 3.0. Pretty scary. A little bit dated here, but 85% of all the traffic loaded into Chrome was HTTPS. Some SSL labs, this is obviously from a TLS perspective, 32% of sites have some inadequate security, at least from a cert perspective, et cetera. So check it out, 21% of Alexa top 100,000 websites don't use TLS. 68% of websites out there still supporting TLS 1.0. Now that's a little bit dated as well. Hopefully that's gotten down. You got still 1 in 10 malicious sites, a bunch of unencrypted traffic. A data point that I thought was interesting is that there's no real, I couldn't find real good stats, but Diffie-Hellman key exchange, elliptic curve Diffie-Hellman ephemeral, adoption continues. Don't have firm stats that are across all aspects of the internet at this point. There's anecdotal from what the browsers are reporting, et cetera, but we know that not all traffic is browser-based. But TLS 1.3 is growing. Cover that in a second, as is elliptic curve Diffie-Hellman with TLS 1.2. It's the standard for all cloud services. Pretty much every web hosting service. We're seeing it in our business everywhere. So Diffie-Hellman key exchanges everywhere. Now, an interesting thing is the IETF site on this, the TLS team. Some fun, a little fun graph here showing the mix of traffic and TLS versions. And they note that it's being broadly driven by the fact that all of the major libraries and languages and certainly browsers now support TLS 1.3. So the idea of just moving to it is natural. And they see it coming and being forced also through the adoption of Quick. Certainly all 5G seems to have TLS 1.3 embedded, and there's more of that coming. So I just thought that would set us off with some basic stats, not necessarily a question, but at least give us a little bit of a baseline to get us started. So let's move into the first question. And it's interesting, we present this all the time, but people still say, okay, so wait, what are all the methods that I could use to look at encrypted traffic, or what we call decrypted visibility? To do that though, let's make sure we cover the basics. I'm gonna cover the basics. I've done this before. The way we see it, it's fairly simple. TLS has two components. There's the handshake, whose purpose is to authenticate, negotiate the cipher suite, and ultimately go through a key exchange. And then ultimately you move to secure communications, bulk encrypted to and from between a client and a server. What that looks like is a public-private key pair on the server that actually you go through a handshake. I think this is a 1.2 basic RSA handshake. I'm not expert on the exact variants, but there's some minor variants based off of the version. But ultimately, the result of the handshake, you start with public-private key pair, you go through a handshake, ultimately to arrive at a trusted connection with a symmetric key. And a symmetric key is a key that is unique per session, it's temporary or ephemeral, and it's mutually shared. It's on both sides of the client and the server both have it. Why that matters is that with that key then, after the handshake, the client and the server can move to hardware accelerated bulk encryption and decryption of their conversation, all using that symmetric key. And so with this basics, I think it's really important to note, again, that the symmetric key, to just be very intentional, this yellow key is not the red key. The red key is your server's private key. It is a master key, if you think of it, that is used for the creation of every session. The symmetric key is unique only per session, and it is ultimately used to encrypt and decrypt the traffic. The second thing that's obvious from this picture is that the handshake stuff on the left is radically more expensive from a compute, energy cost, time cost, et cetera, than the thing on the right. The thing on the right, the bulk encryption, is essentially one instruction set in most chips today. It's how we're able to run here with full motion video with you all here in a multicast scenario. So without our machines dying. So with that background, let's talk about the basic methods. Now the methods are separate than the products, and it's really important to understand that. So the way we see it is that there's methods that are employed in different products. And in fact, if you take a modern next generation firewall, they might employ 3 or 4 of these different methods, at least 2 or 3, as options depending on your scenarios. But so inline systems, whether they be firewalls, web gateways, IDSs, IPSs, visibility appliances, or in out-of-band transparent proxies or visibility appliances, whatever they might be, there's really 4 fundamental methods that we see out there. I'm sure there's a bunch of corner case stuff, but one is man in the middle. And what man in the middle is, of course, is that you actually insert a man in the middle. You tell the client that you're the server. The man in the middle system tells the client it's the server and tells the server it's the client. And it actually terminates the sessions on both ends and bridges them together. I'm sure there's better language for that, but that's essentially what happens. And then therefore it exposes clear text in between and allows you to inspect that traffic and see into the payloads. The second method, which really is not necessarily a method, it's more of an architectural legacy, which is when TLS used to be very slow, a lot of people wanted to offload it from their servers when it was compute intensive. So they'd move it off into load balancers. And so load balancers, typically it's done there, can terminate early the session in front of the servers, and thereby it acts as the server. Your application delivery controller, your load balancer, becomes the server, decrypts and terminates the session, exposes clear text, and sometimes re-encrypts it, sometimes with a lesser level, so that there's at least some level of end-to-end encryption. Very limited in terms of its use cases and scenarios. The third one is passive intercept, and this is where you tap or mirror or span traffic between somewhere on the network, and you send it to a system that essentially you load that system with your key pair, and it regenerates, it replays the handshake and it regenerates the session key, that symmetric key, and then that symmetric key is used to decrypt the traffic so that you can inspect it. Now, I've always talked about these three. There's one more that we should cover. We've been asked about it. I'll just cover it here for completeness. It is, there's a lot of names for it, or people describe it differently, but it's host clear text intercept. And this is where you basically build code shims or modify your TLS libraries or put a system into debug mode, literally to suck out code after it leaves the TLS process and before it goes into your application, or as it goes into your application code, to pull out clear text. So those are the four fundamental methods. I suppose the fifth is that we've actually run into a large number of companies, and especially in the cloud, in cloud applications, public cloud, where people are like, these things don't work for cloud scale, right? They don't work for lots of different reasons. I'm skipping this altogether, and I'm going to try to figure out how to do security and monitoring through app logging and flow analysis. If you're doing that, more power to you. That's not the business we're in. We're in the business of enabling full packet visibility. But at least those are the four methods that we see, the five approaches as they manifest into different products. So the next question that comes up is, well, explain to me, and this was a specific question on the last one that I did, which was why can't passive systems see into PFS or Diffie-Hellman traffic? So let's cover that to be very specific. So this is a very generic conceptual view. Every product implementation, every vendor will probably show you 9 ways to Sunday of how this is. Theirs is far more sophisticated than this. But logically speaking, if you have an out-of-band system, a passive system, whether it be a appliance or a blade in a packet broker, or a feature in a packet broker, or you have a tool that actually does a monitoring tool, application or security tool that does decryption of traffic, typically this is what happens. There's really 2 engines involved in the decryption part of the equation. You basically send traffic to the system and you load this system with your public cert and your private key. And the system replays the handshake and applies the private key ultimately to recalculate and rediscern and capture the symmetric key from each session. And that symmetric key then is actually played into a bulk decryptor with the traffic again to ultimately produce clear text. Now, if this is a dedicated decryptor, that's all there is. If this is embedded as part of a tool, then it moves into the tool system for all of its inspection. Now, obviously, there's certificate management. There's all sorts of policy and features and knobs and buttons on how to do this, but this is the basic thing. Now, the challenge is that, and this is fine for traditional traffic. The problem is when you introduce the Diffie-Hellman key exchange, and I do not have time, nor am I expert enough to actually describe it in full detail. But there's plenty of great resources from a lot of people out on the internet, videos as well as documents, to understand the Diffie-Hellman key exchange. But fundamentally, the result of the Diffie-Hellman key exchange, which, by the way, sometimes people use the phrase PFS or perfect forward secrecy, or Diffie-Hellman ephemeral, or elliptic curve Diffie-Hellman ephemeral. The end of the day is what this key exchange does is it actually eliminates the ability to derive the keys from the handshake anymore. In fact, you can't derive the keys at a band at all. That's one of the fundamental features of Diffie-Hellman is nobody can spy on you, steal your public-private key pair, and then unlock all the traffic in perpetuity. So you can't regenerate the keys, therefore you can't decrypt, therefore you can't get to clear text services. And this is Diffie-Hellman is part of the TLS 1.3 feature. And as we mentioned, we see it everywhere showing up now as a base standard with TLS 1.2. So this problem, you do not have to wait for TLS 1.3 to become your reality. It's probably hitting you more and more. There's one last note here, which is a statement of obvious, which is this system here never worked in the first place if you didn't have the public-private key pair. So very specifically the private key. So why does that matter? Well, if you don't own the server, you don't have the key. And because I don't think Google's going to give you their key, or XYZ or Netflix, or you name the service on the internet, or the third party, or Amazon. So the idea of you applying this mechanism to traffic to third-party servers or services, it never applied. It was only applicable in a limited fashion, and now that's being severely crippled unless you don't adopt the highest levels of security. You can turn down your security and this system still works, but if you are moving towards a TLS 1.3 world or an elliptic curve Diffie-Hellman world, these systems are becoming obsolete. The reduced functionality and their lifespan is going away. And the sad part is it's not just the system, it's the downstream tools and the processes and the systems that depend upon this mechanism that actually get injured in this process. So hopefully that clarifies that question of what's going on there. So the next question is yeah, okay, so what about inline systems? So why do they take such a performance hit with modern TLS? And so I'm really going to focus on man-in-the-middle technique because man-in-the-middle is the primary mechanism that's used. So this is, excuse me again, for anybody out there who makes an inline system or loves inline systems, this is a very sophomoric view of a next-generation firewall or a web gateway. Let's just say it. Let's just call it a secure web gateway. It has some basic services. And let's say those basic services is URL filtering and web reputation. Doesn't require decryption. But if you want to apply any deep packet services like DLP, like signature-based packet inspection, like sandboxing or whatever it might be, malware analysis, et cetera, you have to unlock the traffic to see it. So the way these systems work is you send traffic in, and basically, without going into a lot of detail, the client says hello to the server. The system lets the hello through and then waits for grabs the response and then puts a proxy response to the server. The server responds to the certificate. This man-in-the-middle machine overwrites the certificate and says, and rewrites the CA saying, I'm the server, not the other guy. Client, of course, has to trust that. Then it goes through this process of the client handshaking with the man-in-the-middle server, and the server man-in-the-middle's client synchronizing with the server. Now, essentially what we're doing is we're inserting another handshake. And if you recall, we talked about handshakes are really expensive. They take time. They are not this high-speed bulk encryption. So you're inserting a server and a client-side handshake. You're inserting the encryption and re-encryption of traffic, but you're also inserting that in line normally. And you're adding, most importantly, a sync state machine, which is, it's not just I terminate and then I re-establish and I just bridge the two together. They have to be coordinated and proxied through a state management and synchronization machine. And in fact, that's one of the reasons why when TLS 1.3 came out, why a lot of these systems broke, because those machines had to be completely rewritten and reprogrammed, especially if they were hardware. So the reality is that this man-in-the-middle process is why, and this weight of this, by introducing another handshake and introducing the sync state, is why when you turn on full packet inspection on, let's say, a next-gen firewall or an IPS, it can drop to 10% throughput. So what does that lead to? It leads to you saying, well, I need to hand engineer and bypass all the traffic except for some traffic that I want to respond. And it sends you down a very expensive path of tinkering of traffic. It also has a problem in that there's a lot of systems and a number of applications that burp on this process, from the latency that it introduces to the certificate rewriting. But that's basically it. I mean, this is why these systems, the weight of this man-in-the-middle process and function is really heavy. That's it. And you pay for that in terms of price performance. It's that simple. But hopefully that answers that question. So let's move on to the next one that's related to, they kind of also go in sequence here. So then what are the common challenges that people are dealing with? And I've covered this again, but also I'll fly through it. So in the man in the middle, we covered it, performance, but there's also more and more like PIN certificates, which is basically the app does not permit you and will not accept a rewritten certificate. Or you pushing a new CA into the app. And what are those apps? Everything from Microsoft, everything from Google. Pretty much every mobile app now is coming out pinned. So pinning certificates is actually problematic. There's also a bunch of protocols and systems that have sequencing problems and latency problems that the man in the middle is troublesome for. There's also just fundamentally a move to shut down. If you actually read the TLS 1.3 specs, one of its features is inhibiting man in the middle. It's marked as written and documented as a feature. Now, obviously, the industry continues, and it's actually been a feature of every evolution of TLS, which is trying to shut down man in the middle. But I just thought I would call those out specifically. We cover the ones on the right, which is this X thing doesn't work with man in the middle and you needed your third party. And there's also a lot of certificate management that's here. And with the termination offload, this is limited for not necessarily for microservices architectures or east-west traffic or outbound traffic. There's some regulatory issues of doing this, and again, a lot of certificate management changes. But overall, what we hear and where we engage with people is that all of this is just complicated. It's hard. And in fact, most customers have to have a mix of all three of these mechanisms because none of them work ubiquitously. And they represent complexity and disruption to application and DevOps, et cetera, et cetera. So those are the problems that we're generally seeing. I'm checking my time, so I'm going fast, so I'm just going to keep flowing through those. And Mary, again, any questions coming in that I need to clarify before I move into the next chapter?
We have one question, Steve, but I think it'll be better at the end as it's pretty deep technical. Okay,
sounds good. Hopefully I can answer it. All right, so let's move to symmetric key intercept, this stuff that we've been talking about, that the new method. So let's restate what it is. And then we'll go into some details about it. So symmetric key intercept, the basic idea is that if you want to, is around this. You want to look, let's start here. The business need, you want to look at payloads. The challenge, all your traffic is encrypted, and it's being encrypted with these new levels that actually cause havoc to existing systems. Great, so there's a change in the world that you need to deal with. So if you step back and say, well, if the old methods aren't working so well, because interestingly enough, those methods were all invented, 10 years ago plus, and TLS keeps on marching forward to improve security, but you can't revise the methods so far. You can only take them so far. The idea here is they're a different approach. And so if you break the problem down, to decrypt traffic, you need the encrypted packets and a decryption function. And decryption itself, as we've covered, is commodity. It's really efficient. The hard part in all of this is getting your hands on the key. Right? If you think about it, you put in a whole man-in-the-middle machine just to get the key, to unlock the traffic to look at it, to only re-encrypt it. You terminate traffic early just to get the key so that you can look at the traffic. You actually and change application architectures and integrity of end-to-end security. Well, the out-of-band doesn't even work so much anymore. So the question was, as we stopped and we said, as we were trying to tackle this problem, what if you could get the symmetric keys another way? And it's fairly simple and sitting right in front of everyone. And really, it was born from us really starting our business born in the cloud, though this applies anywhere to cloud or data center or hybrid. There's a fundamental fact, which is the client and the server, when the session is alive, the key lives in the memory. It's the same key on either side of the connection. TLS client, TLS server. Now, this could be even a server-to-server connection or a server-to-a-service connection. Doesn't matter. The key is on both sides of the connection, and it's living in the memory during the session. Sometimes they're kept around for a short while for resumption. After a while, they're cashed out and thrown away. Simple question, simple idea. Why not capture them and reuse them instead of spending all this money to rebuild them or reestablish them or recalculate them? Or why add more handshakes, which represent all sorts of nightmares? So our whole basic idea that stimulated this whole thing was, what if you could capture and reuse those tools to fuel decryption systems and unlock visibility for the modern era of TLS? It's really the fundamental idea. And that's essentially what symmetric key, the symmetric key intercept is. We are intercepting and capturing and reusing the symmetric keys. So what we have built is a suite of endpoint microservices and agents that you deploy on your servers and or your clients, and they know how to discover and extract symmetric keys to intercept them and distribute them to various decryption systems so that your decryption systems can efficiently and effectively get to clear text. And the system, and we'll cover it, it's been the idea of getting your hands on symmetric or session secrets is not new. There's lots of people doing it in debug mode and for DevOps, et cetera. But what we've done is we've created a reliable system that's secure, that's very efficient, that's economic, and that is massively scalable. And that doesn't involve any changes, that works no matter what protocol or session type, whether you're the client side or the server side. It works without changes to code or libraries. It works without any involvement of PKI or changes to PKI, because it's a different key. We're operating at a different level. It's really, really a different method that we've introduced with this. And so one level deeper, what this looks like is you deploy key sensors on servers or into Kubernetes or container environments, or even now we've introduced support for client and soon mobile. You deploy a sensor onto one of these systems on either end, wherever you can get a footprint, and it discovers the keys. And then it delivers those keys lightning fast over encrypted connections to either inline systems like firewalls and IPSs, or to out-of-band systems like a IDS or an application monitoring system, and or ultimately to secure key archives that could be used for lawful intercept or archival forensic capabilities and compliance capabilities downstream. And when it delivers those keys, those systems can now operate with pure symmetric decryption and eliminate all the handshaking, all the key replays, all the blind spots, et cetera. So that's essentially what symmetric key intercept is. Hopefully that clarifies and makes it more. So it's really, for us, it's all about the keys. It's all about getting the keys. So how do we get the keys? It's probably the next big question as we present this. People, once they kind of grok that and they say, okay, I get what you're doing. How do you do it? How do you really do it? So I'm going to peel the layer back one level that we haven't before. So hopefully this will be new for y'all. So this is again, very generic, very simplistic, but I think it's very conceptually accurate picture of a TLS session. Actually, after the handshake, a session is set up where connection, let's just call this the server, but it could be either side of the connection, client or server. Inside that host, whatever the operating system, there's variants based off of every operating system, et cetera. There's memory. And inside the memory, there's an application. And that application processes using a chunk of TLS code. It could be a library, it could be statically linked, it could be statically embedded, doesn't matter. There's a chunk of TLS code whose purpose is to manage the handshake and ultimately maintain the connection and terminate the connection and export clear text into the application code. And to do that, it has the symmetric key that we've been talking about. So, so remember, the session doesn't terminate on the NIC, it terminates inside on the TLS code itself. There's lots of security measures around that, et cetera, but at the end of the day, it terminates there, and using the key, it's decrypted and the symmetric key for that session, and that session then is piped into the application code. And what we've done is in our core IP, as we have perfected the code and the ability to place a read-only sensor, a system, a piece of code into that memory that knows how to read the keys out and extract them. And what's very specific to us is we've not only written this code that can do this and essentially hook into memory and pretty much, well, all Linux and now Windows variants, and now working on mobile and OS X, et cetera, but also the ability then to have understood algorithms based off of the types of TLS that happen. So what this is a read-only memory tracer that's running on the client or the server, and does not alter memory. It's literally just a read-only memory trace. And it doesn't change the applications or et cetera. You literally place it on, it's a silent read. And how it works is this. This is what I was trying to get to. You actually, the system, when it regularly scans the system to discover TLS variants. That's IP number one, is we know how to detect TLS variants running in process memory. Second is it loads in a suite of signatures or the appropriate signatures for the variant. So it's OpenSSL version 1.1.3b FIPS variant. Okay, great. There's an algorithm that represents a set of very defined targeted hunt rules for where and how that TLS code will work. We have approximately 900 of them today, covering about 98% of all TLS libraries and scenarios out there. We're continuing to expand that. And what happens then is it loads those in, just the ones that it sees. So it's very efficient. They're compiled little runtime codes, and the system, when it sees a client hello, meaning the start of a handshake, it actually then knows where the final key will appear in memory offsets. Now, sounds really simple, but it's very, very complicated, very, very sophisticated in how we do. We have patents on that. That's how we do what we do. But once it does that, it copies the key. We'll talk about what it does with the key in a second. But the beautiful thing about this is that we don't care about the handshake. The handshake in between. We see the beginning of the handshake, we know where the final key will hand. So we don't care about handshake, we don't care about protocol versions, we don't care about cipher. It works for TLS 1.3, 1.2, 1.1, 1.0. Et cetera. It's extensible into new libraries. We're constantly looking for, we're growing our footprint into new libraries, but also new variants of new versions of libraries release, and we immediately then turn those out, typically in less than a week. And the beautiful thing also is you only have to be on one side of the connection or the other. Remember, the key is the same place. And with that key, I can unlock the traffic wherever I grab the traffic. The last piece here is the performance. The sophistication and the uniqueness of what we do is pretty killer. We can get that key in under 120 microseconds on average. To give you an idea, handshake is what, somewhere 200 milliseconds to 2 seconds, depending. So we can actually get the key dozens of milliseconds, like 20 or 30 milliseconds before certainly the first handshake, the first encrypted packet's even sent, and we can export it out of the system. So a benchmark of how fast this can go. We're growing our benchmark set, but essentially if you take a reference thing as an AWS C5 extra large, running it on a good day, it compressed 600 keys per second. We can grab all 600 with less than 28 mega memory and less than 0.5% CPU core. That system scales up, it scales down, and it's because we're not doing massive memory grabs. We are literally very laser targeted differential rules on how to do this. And so it is a very lightweight process in both memory as well as CPU, and as I said, reliable and efficient. So that's how it works. I'm sure you'll have questions about that, but let me just plow through these. So once you get the keys, what can you do with the keys? This has been expanding as we've we're now engaged with over 25 manufacturers of tools and systems that are looking to support TLS symmetric keys and from us to be able to supercharge or refuel their tools and their systems. So our options for key consumption have been rapidly growing, maybe even since the time you first started looking at us. So what can you do with keys? So the sensors get keys, session keys, and what do we do with them? One, we can actually write them to a local file, and they could be picked up by something like Wireshark or anything else. We can actually write those through customization. I mean, it's a custom, more specific to manufacturers, but we can write the keys and pipe them to another application or process on the same system. So imagine you have a host-based IPS. We could actually be feeding the keys now, and that host-based IPS actually could be doing a pure symmetric decryption without having to do man in the middle and slow that host down. Also could be piped into an SD-WAN client that's actually tunneling that traffic out to an SD-WAN. And now when that traffic arrives, you have the keys to decrypt it with pure symmetric decryption and skip man in the middle. Then also you can export, the keys can be exported outside the system. They can be sent to inline systems, as I mentioned, like firewalls. They're sent over TLS connections. So securely fed to firewalls, IPSs, or web gateways. They can be sent to IDS or passive monitoring systems, or also to dedicated decryptor and visibility systems. Or as I mentioned, folks can direct those into any number of different key storage systems or off to escrows. The last thing is that we also support the ability to do a thing called a key depot. We actually started here, and I want to make sure, and we'll cover this more with the Q&A, is that the key depot is actually intended to be an aggregation, control, and distribution point, not a database. It is designed to be a relay point, hence why we call it a depot, not a database. But it is implemented with a database. It's actually implemented with a short-lived database, meaning you set the time to live, and typically it's 1 minute for a key, because if you don't capture a key, there's no reason to keep it. So you grab the sense you're capturing the symmetric keys, you hold them there long enough to be utilized by a system, and then you discard them. And then this system allows massive scaling in the distribution and support of multiple push-pull environments to multiple different systems that you see above. So those are the key options, and those might even be expanding as we move forward, but pretty exciting in terms of what that does. So let's talk about some use cases and put this into action, and talk about the scenarios of how this really comes into play. And I sketched this out last time, but now I have some nicer pictures. So one of the things here is that let's talk about an outbound traffic. Your enterprise, you've got a data center, you've got, or even you've got employees going out, and you've got a web gateway. Or whether it's implemented in next-gen firewall, and IPS, DLP, whatever it is, you've got some inspection on the traffic on the way out. You don't own the servers on the side, so it's clients. Well, and remember, this actually could be servers talking to third-party services on the internet, or even Amazon or AWS or GCP, or it could be your clients going and talking to Microsoft 365. Doesn't matter. Performance from this man-in-the-middle machine to get the deep packet services, blind spots, and it's complicated, management and operation. So what the manufacturers are starting to do, and we're starting to work with them to basically take keys. We can put the sensors on the clients or the servers on the inside, and grab the symmetric keys and forward them to a symmetric decryption function that is inside this inline device, and enable pure symmetric decryption, and thereby get to line rate level performance. So the promise of this that we're working with manufacturers is a symmetric key intercept can actually move you to line rate full packet inspection, and at the same time not have things that you can't see into. Exception now becomes a compliance discussion, not a can you do it discussion, and a radical simplification, because there's no more certificate management on this device, or anything else, or trying to manage it. So that's one view, and the view is the same. If this was a firewall for east, west, or inbound traffic, the only difference is you can get keys from either side, wherever you have a footprint. If you control the servers, now you can actually grab the keys easier from the servers than messing with clients on the client side of the connection. On the passive side, so we've got a passive system, and as we mentioned, that key generator feeds the key decryptor with a symmetric key, and we know that doesn't work. So what we can actually do is we can now feed keys on either side of the connection, again, TLS client or server, and feed symmetric keys directly into these. And it's amazing what we found is that most manufacturers have one facility or another to be able to pick up and read in symmetric keys, because that's ultimately what their key generator was doing. It was generating keys and feeding them to a symmetric decryptor. So now we can actually bypass that and the key management and ultimately get to seeing all the PFS traffic, but for the first time now also be able to apply out-of-band to traffic where you don't own the servers and you don't have the server keys. And again, this impacts performance, cost, simplification, product lifespan, et cetera. And we can affect this a number of different ways. We also, as we've talked about before, we have a generic container decryptor that we are providing to manufacturers or to end users that they can embed on these tools. There's lots of different options. The same story happens as if this is a visibility appliance or a packet broker. The only difference is that now it's decrypted once and can be distributed to multiple tools. It's not just the tool itself. Same benefits. Now, here's an interesting thing that pulls it all together. In a hybrid environment, let's just say you wanted to do analysis of a high-speed link between two servers, and let's even get fun. Let's high-speed link between a server talking to AWS. Let's say this writing to an S3 bucket or to a DynamoDB over here. Well, you're not going to be able to get the and multiple services. You can grab the keys from either side. And instead of trying to turn on man in the middle, you could just do your basic filtering services with your firewall. And then you could actually do and move and start to augment or offload some of those services to out-of-band for the first time. I mean, this has never been possible because you didn't always own the server keys, and because performance-wise, the out-of-band systems were fairly expensive, and with pure symmetric generic decryption, you can go markedly fast. Now, the reason why I showed this picture, of course, you'd say, well, wait a second, I was looking for active protection. We had one customer and said, yeah, but I can feed the alerts from a passive system into my SIM, and my SIM can drive a block or an action tomorrow, I mean, in near real time. So you can essentially restore five-fold bandwidth and throughput to some of these devices that are becoming blocked through man-in-the-middle function, and augment it with out-of-band. And here's one last variant of that: is simply decrypt it on the side and actually shove it into the system's IDS import. And now you're still utilizing the same tool and the rules. You're just doing it in an IDS fashion versus an IPS, and again, being able to move back to wire speed. And thereby reduce costs and extend life and investment to end users. And for the manufacturers, it improves competitiveness, right? And value to their customers. So hopefully that covers kind of a swath of use cases and implications. So obviously some of these, you need your manufacturers, and we intimated that last time, you need your manufacturers to support, but some of these you don't, whether it be placing your own symmetric decryptor on your tool from ours, or working with your packet brokers who could enable lots of tools, or even ultimately starting to offload it to out-of-band systems or even open source systems. That's our path now, is we're helping end users as well as manufacturers start to adopt this new mechanism and method. So hopefully that covers it. Now we get to the big questions here, and I'm going to go really fast. I'm watching my clock. So there's usually three big questions that people come to. We've been doing this now for a while, and the three biggies are this. Wait a second. I now fully understand what you're doing. Is this a hack? This doesn't seem right. Oh, I'm digesting this. This is new, and this doesn't, is this a hack? The second one is doesn't this go against the concept of TLS? What are the TLS gods going to think? And lastly is what about operating systems in the libraries? Can't they just shut you down? So let's cover each of these, because these are really the three, if you're really evaluating the method, the strategy versus the implementation, these are the three big questions, followed by security, and we'll get there in a second. So let me cover these very quickly. It's not a hack. This is not a piece of malware. This is a purpose-built piece of software that only functions if you give, if an end user who legally controls an endpoint, installs it, and provides explicit systems permission to that piece of code to be able to read memory processes. And that's very different than a piece of malware that just does that on its own. So that's the first part. That's very, very important. So we don't look at it as a hack, and ultimately once you start to grasp that, you'll understand that's very different than a piece of malware. Second question, does this method go against the TLS mission? And actually the reality is no, it's actually more true to the TLS mission than, say, man in the middle. So really, if you grasp this too, and again, it's kind of, you go through a wave of understanding a new disruptive technology. It's actually more true to the mission than the other methods. If you're the legal owner of an endpoint, you have the legal right to look at the data. All this does is extend the location of where you can look at it. And this is slightly different or markedly different than what you see with man in the middle, where you're modifying certificates, you're interrupting and spoofing traffic on both ends, you're repurposing server keys in some of the other scenarios. As we talk to some folks who are in the know, it's just different. And I'll let that just set with that. I mean, in long term, one could argue that every one of these things that allows you to look at encrypted traffic, but we're not doing it in the middle. We're actually enabling you to do it from the sides and the ends, which again, I would argue strongly is true to the TLS mission. And that gets to the last part, which is related to that, which is this is actually method is embraced by the industry. It's the contrary, which is, hey, once the industry figures this out, are they going to shut it down? So there's actually many people that are doing and getting you symmetric keys today. You have an F5 load balancer, it can log off keys into little key files. People pull those off all day long. Most browsers today, actually, in libraries, you can put them into a debug mode and log keys. You just don't want to run them in production. Riverbed has released an API as part of their latest Steelhead app response product that actually can receive keys. ExtraHop is doing some things in this area. This is not a new idea. And it actually seems to be growing support versus shrinking. And the fact that every major browser from every operating system actually supports key logging and actually has been expanded and documented actually it shows the contrary. The second part though is that, wait, but the operating systems, they might want to stop you from hooking into memory the way you do. And the answer there is actually the opposite too. Every operating system manufacturer, there's only a few, right? They are actually going the opposite end, and the functions that we use to hook into and trace memory is the same types of, not the exact, but the same type of functions that are used by endpoint security and in EDR functions, by application performance monitoring and modeling software. Every operating system has hooks for operational memory tracing. And in fact, there's move to formalize those into open standards bodies more so than them being unique and discrete. They've been in Linux since early BSD era. So it's actually the opposite. I just thought I would share that with you. The issue is that Nubeva has actually taken these methods that actually seem to be out there as a bunch of DevOps kind of quirky little tools, and we've just perfected it as a production-worthy system. It's fully functional and scalable and something that somebody can depend upon versus it being a set of developer tools. So hopefully that answers that, but that rolls to the next question. What about security? Darn it, I got to go fast. All right, so let me go cover this. This is going to be really fast, so I apologize, but what about security? So that's the next question. All right, so there's 7 points, I think there's 7 points of security I want to cover. First, symmetric keys have a radically different footprint than server key pairs, much lower. It's one key for one session. And you need to have the data. So if you lose a key, it's not like you lost your whole server integrity. You lose one key to one session, and you have to have the exact set of packets for that one session that was what? 2 seconds long, 2 minutes long? That's it. So from a key perspective, versus the management of that precious key pair, server key pair, which is the keys to the kingdom, is a radically different, lower risk footprint to start with. That's the first thing. The second is key delivery. Keys are never handled on clear. They are grabbed and they are only handled around through encrypted tunnels. Obviously, if we're sending to a local file, that's different. But as we're sending them off to tools, it's always done inside encrypted tunnels, always inside the customer's network, always utilizing the customer's security so they can scope and limit that as much as they want. Third, key depots. Key depots, as I mentioned, they are optional, first of all. Second of all, they are private. They live inside a customer's data center or their cloud. And they are not intended to be a long-term storage database. They are a database that is used as a short-term, short-lived buffer and distribution point for keys to serve multiple systems. That's it. You set your time to live, as I've covered. So it's really a scaling and control function more than it's a security and risk function. Obviously, if somebody taps into that thing and was copying your whole database, but you've got larger issues if people are able to own entire databases. But it is part of the security discussion that we have as we architect solutions with our customers. Key extraction. We are not doing mass memory exports. we are literally doing a surgical grab of some 300 bytes at a given offset. So we're not even pulling out memory, out of bulk memory out of systems. So all we're doing is pulling a key and actually the client random, that if you have no data or knowledge, it's relatively useless information. So that brings in the next part, which is the key plane. Something very interesting architecturally happens in this solution. We separate, in all other solutions, you derive the key with the traffic through man in the middle, through early termination, et cetera. So you basically put the data right with the key for somebody to be able to discover or play with. If from a security perspective, we actually separate that. The keys are completely separate from the data. So we actually create another layer of abstraction of security, because somebody has to put the two together and have access to both to be able to get to be able to decrypt. Again, a different risk profile altogether, much lower. Key sensors themselves, they actually have no inbound communication ability. They only function on outbound rest only to a destination that you pin it to. And ultimately, again, in your control through your configuration, cannot be altered once you set up and configure that. And then the sensors themselves are hardened with regular vulnerability scans. And the last part is the signatures themselves. They're actually, the logic is coded into binaries. They're not copyable or to be exploited. They're intentionally obfuscated, so they're not like a set of signatures that shows a hash. They are actually very distinct IP that is actually hidden in coded binaries in C and Go. So, and they're cached actually into the system via management repos versus continually hard coded into the binaries and the sensors themselves. So hopefully that covers some dimensions of it that's pretty thorough as you start to comprehend the architecture of what we're doing. Scaling, I think we've covered this before. Sensors can operate in parallel, so they can, each one of them, let's say doing 1,000 keys a second, you have 10,000 sensors. We just did a quote for a customer doing 1 billion keys per second, per month, being sent to in their case, it was a DynamoDB in Azure, and I think the cost was like $1,600 a month for the DynamoDB. But then that was able to serve scale up and scale out of decryption systems all day long by not having to worry about landing the keys on the same place as the packets. Instead, the decryptors can simply pull the keys when they see encrypted packets landing on their interfaces. And very important for things like 5G and massive scale operations. So one last one that was here, and then we'll get to open Q&A. Service mesh. Service mesh has been talked about. I am not a service mesh expert. I know a little bit. I'm going to try to dumb it down and at least hit it at a very high level. So if you think about it, the basic idea of service mesh is in front of every container or set of containers, a pod, you actually put a service mesh proxy. Yes, it is a proxy, and it advertises services, and it's controlled so that you don't actually, you can connect services versus other things. That's not the point of the conversation. The end of the day, a TLS connection comes in and it needs to talk to a container. It goes through a service proxy. As a inline device, you only have primarily 2 mechanisms traditionally to get that traffic. Option 1 is turn on man in the middle, in which case that service proxy will slow down dramatically. It will not be able to handle any PIN certificate traffic. It will not be able to, you will have a second issue, which is how are you going to handle that clear text traffic and exporting it around your environment? And lastly is what's the management over that whole thing, because it's not built into a service proxy world. The second option is you could terminate right on that service proxy and leave it encrypted into the container itself. Now you're not end-to-end encryption. If this is in the cloud, you have clear text running around on the backbone. You have to figure out, again, how to handle the exporting of that traffic off to your tools, and of course the system management. So service mesh is just in line. It's just using a soft proxy versus a hardware appliance. It's the same exact game. And so where we introduce the opportunity that we introduce into this is introducing, sorry, it's a little bit added to here, but that service mesh or those pods are running on a node underneath the Kubernetes cluster and a VM. You would deploy a sensor as a daemon set, just one per node. and it is capable of capturing all of the keys out of all of those containers for all of those sessions without putting the service mesh into a man-in-the-middle mode and slowing it down or decrypting traffic prematurely. It also allows you to run it full TLS 1.3 in this whole thing. And so we can grab the keys, and wherever in the network you want to tap the traffic, you can rendezvous the two on your decryption systems and thereby decrypt, inspect on your visibility systems. And the benefits of here is no production, mods to production traffic, little performance load, works for any kind of session, dramatically lower cost, ultimately compute costs, and enables full visibility of a service mesh environment. So hopefully that covers a swath of all the questions. Now, Mary, I did this, I got 5 minutes. I went as fast as I could. Hopefully that answered a bunch of questions. What other questions have we got?
Yeah, we got first question I can answer. Can we get a copy of the deck? Yes, we will send a downloadable copy after the session. Steve, we have two, and Eric might be good at one of them, and so I just let you know it's a little bit technical. Does tapping work in the network interface using DPDK or SRIOV?
Tapping.
Yeah, I can answer that. Yeah, not today. You know, whoever asked that, we'd love to hear some of your requirements around it. But today, based on the instantiation with the virtual tap, it's actually looking at what's crossing a Docker bridge. So if it's not crossing that, we can't see it today. Doesn't mean we couldn't potentially, just not today.
Yeah. And I think what he's referring to is that we have well, we'll just leave it at that. I know. Let's get to the other question.
Cool. So the other question was on the key slide, Steve, the different deployment options.
Okay. Let me go back and share this in this mode so I can hop around, I think. Okay, so what's the question?
So the question is, pipe key to a local app or agent, is it a shared container, pod? What is the API?
So actually this, if we are doing this, we have not published a formal third-party API. This is custom integrations that we are working with a number of vendors on right now. If you are a vendor asking that question, we actually have the ability to do very specific integrations here so that we can, everybody's, of those that we're working with, everybody has a different requirement, and we have a lot of flexibility for how we can export those keys through an API, a REST API, through a true programmatic piping. It depends on the level of engagement we really want to have. This, in the long term, people, if you're end user asking that, the potential, yes, is that we are trying to move this to become a standard method that's supported, and that is a option that is has broad industry support, so that you could go and say, hey, Mr. Host-based IPS, do you support symmetric key feeds? And they say yes, and you say, great, I've got my new Beva sensor, I'd like to set it up and feed it to you and flip you into passive mode or into symmetric mode instead of man-in-the-middle mode. That's where we're headed. So hopefully I answered that question depending on where you're coming from on that. Hopefully this gave you, Mary, more questions there?
That was the question.
So it tells me we were thorough, or you're not interested, or you're bored, or we covered it all. I mean, hopefully some of these new views, and for those of you, again, I think some of you have been on a number of these, you're seeing rapid innovation and evolution. As I mentioned, we've got an extreme spike happening in an end user takeoff on this, as well as manufacturers starting to say this is a game changer. I mean, just if so again, if you have a manufacturer, and we expect to start having some announcements starting to come of people joining our Alliance program in the coming quarter. Those are all coming together nicely right now, with products starting to be released in the coming quarter, in fact. And so if you have a manufacturer and a favorite tool or a system that one of these guys over here on the right, tell your people that they should get on the train. That's my objective here, is to evangelize this a little bit, which is, if you think about this, just the closing thing, there's not a lot of other options, right? I mean, man in the middle is expensive. and trying to keep that running and put it everywhere as we move to more and more service mesh and microservice architectures. It's expensive and complicated, and it has holes. And out-of-band is phenomenal, but it's actually blinded right now, and we unlock both of those. And so if you I mean, obviously the downside is you have to put a sensor or an agent out there, but agent technologies have evolved. It's not a driver. This is like a microservice that you load on. You don't even have to restart a system. You turn it on, you turn it off, turn on key capture, turn it off. It's a different thing. If you like this idea, become part of the train, and I think the train's leaving the station. So we're very excited and thankful for you to take the time to come and listen to us. And if you have any ideas or questions outside of this, we'd love to engage with you personally. If not, we hope to have more of these, and we might lighten how many of these we have during the summer, just to respect people's vacations. We'll see how it goes. But with that, I think it's 1 o'clock. Mary, do you want to? So I'll thank everybody, and Mary, you want to wrap it up?
Yeah, thank you, everyone, and we will be sending a follow-up with the recording and the deck here shortly. So thank you all for your time.
Yeah.
Steve?
Thank you very much. Have a great day. Hope you're all safe and healthy. Bye-bye.